Alright, looks like we are live. Let's continue. Let me open the table of content first. Okay, we are still in patching introduction. Let me open that. And currently on homework simulation section here. This one. Before we go further, let me read me, I guess. Patching linear. I think this one. Patching linear translate. Okay. Read me here. Well, let me read from the beginning, I guess. In this homework, you will use a simple program which is known as patching linear translate.py to see if you understand how simple virtual to physical address translation work with linear page table. Okay. To run the program, remember to either type the name of the program like this one, or using the Python, this one, Python command. When you run it with the -help, -h, I mean, it is the help flag, you see something like this. Alright. And then first run the program without any argument. I think this one. Okay. We got something like this, right? Okay. For virtual address, return the physical address it translates to, or return that it is an out of bounds address, a segmentation fault. As you can see, what the program provides for you is a page table for a particular process. Remember, in a real system with linear page table, there is one page table per process. Here we just focus on one process, its address space, and thus a single page table. The page table tells you for each virtual page number of the address space that the virtual page is mapped to a particular physical frame number and thus valid or not valid. Okay, the format of the page table entry is simple. Leftmost high order bit is the valid bit. The remaining bit, if valid, is 0. H1 is the, what is it called? Page frame number. Okay, if, what is it called? If it is valid, the rest, the remaining bit is page frame number. Okay. Yeah, this is from the previous session, right? Leftmost bit is the valid bit, and then if valid, The remaining bit is the physical frame number. In the above example, the page table map virtual page number 0 to what is it called? Page frame number, this one, or decimal 12, and then virtual page number 3 to page frame number 0x6 or decimal 6, and leave the other two virtual page 1 and 2 as not valid. Okay, so this means that this page table have two valid address and two invalid address, I guess. Something like that. Because the page table is linear array, what is print above is a replica of what you would see in memory if you look at the page yourself. However, it is sometimes easier to use the simulator if you run with the verbose flag. Test 5 here. This flag also prints out the virtual page number or the index into the page table from the example above. Run with the SV flag. Wait a minute, be right back. Okay. Alright. Let me try. So the only difference is this one, I guess. Okay. Your job then is to use this page table to translate the virtual address translate the virtual address given to you in the trace to physical address. Let's look at the first one. Excuse me. Okay. Use this page table to translate the virtual address given to you in the trace to physical address. Okay. Let's look at the first one, this one. To translate this virtual address into physical address, we first have to break it up into its constituent component. A virtual page number, okay, and an offset, right? We do this by noting down the size of the address space and the page size. The size of the address space and the page size. In this example, the address space is set to 16 kilobyte. Okay. Wait, what? Hold on. Did my internet connection drop? Wait a minute. The address space is set to 16 kilobyte. A very small address space, and the page size is 4 kilobyte. Okay. My internet connection is back up again. Okay, the page size is 4 kilobyte. Thus we know that there are 14 bits in the virtual address. Thus we know that there are 14 bits in the virtual address. 14 bits. And the offset is 12 bits, leaving 2 bits for the virtual page number. How do we know? How do we know that the virtual address 14 bit? Let me try. Is it something like this? Oh, okay. Yeah, it is the combinatorics, I guess. Interesting. Okay. 14 bits, and then the page size here for kilobyte means that something like this, right? And that is why we have the 2 bits for the virtual page number. What is it called? The power number here, I guess. This is 14 bit for the total of the address space, and 2 bit for the virtual page number. So the offset is maybe something like this. The bit for the address space, and then the bit for the virtual page number, and then the rest is the offset, something like that. Okay. Those with our address with is binary, something like this. Okay, right. If we, what is it called? If we put it like this, this is 14 character or 14 bits, right? The binary digit. We know the top 2 bits specify the virtual page number. This one. Thus this address is on virtual page 3 with an offset. Oh, interesting. So this is the virtual page number 3, and the rest is the offset. Okay. Next we look in the page table to see if virtual page number 3 is valid and mapped to some physical frame or invalid. Okay. If I remember correctly, virtual page number 3 is valid here. The invalid one is virtual page number 1 and 2, something like that. We next look in the page table to see if virtual page number 3 is valid and mapped to some physical frame or invalid, and see that it is indeed valid. The height bit is 10, and mapped to physical page 3. So we validate from the height bit here, from this one. Is that it? And map to physical page 6. Okay. Thus we can form our final physical address by taking the physical page 6 and adding it into the offset as follows. Okay. The physical page shift into the proper spot. Okay. Okay. Or the offset here, yielding the final physical trace. Oh, okay. 6,229, I guess. Thus we can see that virtual address. This one, 3229, translate to physical address 6229 in this example. Okay. To see the rest of the solution after we have compute them ourselves, right? Just run with the test flag or the compute flag here as always. So we need to check the, what is it called? The binary representation. Is that it? Maybe. Of course, you can change many of these parameters to make more interesting problem. Run the program with the -h flag, the help flag, to see what options there are. Okay, random seed, -s flag change the random seed and to generate different page table value as well as different virtual address to translate. -a flag change the size of the address space. Right, we have to take a look at the source code itself on the previous session, I guess. -p flag change the size of physical memory. -uppercase P flag change the size of a page. -n flag can be used to generate more address to translate instead of the default 5. -u flag change the fraction of mappings that are valid from 0% up to 100%. Okay. The default is 50%. Okay. Which means that roughly half of the page in the virtual address space will be valid. The -v flag prints out the virtual page number to make your life easier. Okay. I'm gonna try analyzing this one. Wait a minute. Do we really need to translate this into binary? Maybe not. Maybe we can just take a look at this from number here. I mean 3, right? For the virtual page 3, and then this is also virtual page 3, starting with 3, the number 3 here. this is the offset, and then this one is 1, starting with number 1, and then we are using virtual page number 1, and then this one is 2. Okay, virtual page number 2. Okay, maybe we can do that. Maybe so. Let me do this, I guess. Virtual page number 3. Offset, something like this. Maybe I should abbreviate this. Offset, something like that. And then page frame number 6. Offset becoming this one. Okay, let me check this one. Okay, look like it is the same, I guess. So maybe we will use this kind of representation. As for this one, because the virtual page number is invalid, we didn't need to add the offset here. Okay, and then let's take a look at the question 1 here. Before doing any translation, let's use the simulator to study how linear page table change size given different parameter. To study how linear page table change size given different parameter. Compute the size of linear page table as different parameter change. Some suggested input are below. By using the -v flag, you can see how many page table entries are filled. First, to understand how linear page table change as the address space grow, run with this flag. Okay, so we are not doing any translation first. And use the simulator to study how linear page table change size given the parameter. Okay. Oh, we are increasing the address space, but the physical memory is still the same. What is n again? N flag here. The number of virtual address to generate. Wait, what? So we're not generating any virtual address? Is that it? Interesting. Uppercase P is the page size. Okay. Page size 1K. address space 1 megabyte, or maybe byte, the binary representation rather than the decimal representation. Okay, let me check. Right, we didn't have any virtual address trace. Okay, interesting. Oh, okay. Base table. I think the address space 1 megabyte is a lot, I guess. Right, from 0 and from virtual page number 0 until virtual page number 1023. Yeah, maybe let's use address space of 1K first. Okay, this one. Yeah, I'm just trying things out here. If it is 1K, how many is it? Okay, oh, 14, I guess, right? And then, yeah, maybe we have 10 bit for the, what is it called? For the 1K address space. This one, I guess. Let me try copying that one. Oh, okay. So maybe something like this. To make it 10 bit. Maybe. Okay. And then let's try this one. Oh. Must be a multiple of the page size. Wait. Okay, 16K. This is the page table. Oh, page size is 4K. Okay. If we have the page size 4K, something like this. Okay. Alright. Okay. So we so it is maybe something to fight. If I use 15K, I don't think we can do that, right? Address space must be a multiple of the bit size. If I use 3K, again, physical memory must be multiple of bit size. Alright, okay. And that's why when we have the bit size 1K and the address space 16K, we have something like this. From virtual base number 0 until virtual base number 15, right? This is invalid, this is invalid, this is also invalid. Virtual base number 9 or the index 9, you could say. Okay. Study how linear page table change size given different parameter. Okay. And then maybe we could the space must be a power of 2. Okay. I'm just trying things out. After 16, can we do 18? I don't think so. Okay. After 16, then there is 32, I guess. Compute the size of linear page table as different parameter change. Okay. How linear page table change size given different parameter. Compute the size of linear page table as different parameter change. The size of linear page table. Okay. I mean, the page size is 1K, so yeah, that make me confused, I guess. What is the goal here? The size of linear page table. The size of linear page table as different parameter change. First, to understand how linear page table size change as the address space grow. Okay. As the address space grow. Okay. Well, with this page size 1K and the address space 32K, so it grow something like this, I guess. But Okay. 800. I mean, because the page size 1K, so it gonna have the, what is it called? Whatever the address space we draw, I guess. I mean, if we change the page size to, let's say 4K here, the page table also gonna shrink, right? So it depends, what is it called? The size of the page table depends on how many page size we have, or the size of a page per page, something like that. This is 16 page number instead of 64 page number, right? Something like that. Hello Franklin Watterson, welcome. And the best for studying from Germany. Oh, hello. Thank you. Not deaf. Hello, not deaf. Welcome. Keep it up, man. Alright. Okay. Yeah. I'm currently on chapter 18, taking a look at the homework simulation here. Yeah, I'm looking at the first question here before doing any translation. Study how the linear page table change size given different parameter. For example, this one, to understand how linear page table size change as the address space grow using this flag. I feel like the, what is it called? The 1 megabyte here is too big to analyze, you could say. I mean, something like this. So I'm trying to reduce that into the kilobyte, something like 16, something like this, right? And yeah, what is it called? The page size, the page table size depends on the page size, I guess, and also the address space. How do I explain that? If we have the page size 1 kilobyte, the page table will have 16. Okay, let me try explaining that here. What is it? If we have page size 1 gigabyte, and 16 gigabyte and address space size 16 gigabyte, we will have page table with 16 page number, I guess. something like that. And then let's say if we have page size 4 KB and the test space still the same, 16 KB, we will have, if I understand correctly, we will have 4 page number. Let's try that out. Yeah, something like this. From virtual page number 0 until virtual page number 3. Okay. And then this is for 16 KB. And then if we have, let's say 32 KB, the page number is 32 page number, assuming we have the page size of 1 KB. And if we have 4 KB, okay, 32 here, we will have what is it, maybe 8 page number, something like that. Let me check. Okay, this is 8 from page number 0 until page number 7. Or maybe we can think of it like the index, you could say, from index 0 until index 7, something like that. Okay, maybe that's what we should analyze in here. Maybe. And then we'll, what? Wait a minute. My internet connection dropped. Hold on a minute. Okay, looks like it's going to be back again. Oh, hello, ping pong point. Welcome. How's your day? Hopefully good. So, I'm having final exam in 2 weeks. Oh, good. Okay, are we back? Looks like we are back. Okay, good luck with your exam, ping pong point. Don't forget to study for the exam. Okay. Alright. let's yeah, my internet connection is having trouble again. Is it already not laggy? Yeah, we are back. And I'm sorry, technical difficulties. You know, how the internet connection suddenly drop like usual, I guess. Okay, let me continue to the question 2, I guess. First to understand. Okay. Then let's understand how linear page table change. Oh, as page size grow. Okay. Looks like I'm skipping to this question. Yeah, I mean, again, if we increase the address size, the address space size, right? But this is still the same, then the page size will also be what is it called? Page table size also increase, I guess. Assuming we only have 1k of page size here. Can I cancel you? I guess. Let's start with a k, and then this one is 1k, something like this, right? The page table size increase, and then let's change that to 16k. The page table size increase again to the 16 entry now, and then let's me increase again 32k. The page table size increase again from 16 entry to 32 entry, so something like that. The page table size increase as the address space grow, assuming we have 1k here, but I think it will also increase when we change the page size too. Let me try using this 2k and then maybe 8k, I guess, right? Okay, change this to 16k, right? It will also increase. The page table size also increase as we increase the address space size. Okay. Let me check again with 4k page size. What is it called? 8, I guess. Okay. And then 16k. Okay. It keep increasing. And then 32k. Right. Okay, so maybe maybe the summary is thank you karena pulling all-nighter. Well, good luck with your exam. Don't forget to sleep. Okay, so maybe something like this, right? If the address space size increase, the page table entry will also increase, question mark, maybe something like that. Okay, then let's understand how linear page table change as page size grow. Okay, as page size grow, okay, before running any of this, try to think about the expected trend. How should page table size change as the address space grow? As the page size grow, why not use big page in general? I mean, as far as I understand, using big page can cause internal fragmentation, something like that. So basically, what is it called? Basically, there is waste space if we have too big of the page size, and this waste space is allocated in the page size in the page, so we cannot really reuse it for something else, if I understand correctly. So yeah, if we use big page, the problem is that we might have those internal fragmentation or wasted space, something like that. Alright. Okay, before we run this, let's try the trend of this one. Okay. For the page size 1K, this one we are assuming that the address space is 1M or 1024, and then the page size 1K, we would have 0 until 1023 virtual page number. VPN in here means virtual page number, just some information. The page number, the total is 124, something like this. And then if we have the page size 2K like this, we have 0 until, what is the max size here? be 511. I mean, it is 512, right? But the maximum is n negative 1, something like this. 12, maybe. Let me check the previous trend. $4K and then $8K. Okay, we have to table entry here, and then 4K and 16K. We have 4 table entry. Starting to see the pattern here. 4K with 32K. There is 8 table entry here. So there is that. And then the 4K here. 4K. Let me check. Divide by 4, I guess. Okay. So this means 255. And the total is 156, something like this. Well, let's. Oh, wait a minute. This is 1K, right? Not 1 megabit. Okay. Yeah, so we cannot do this. Let's use 16K. If it is 16K, if it is 16K, let me think. If it is 2K, then we will have. Oh, okay, this is 16. Page table entry, maybe something like this. And this one is. What is it called? X page table entry. And this one is maybe 4 page table entry. Something like that. Okay, 16K. 1K. I had 16 page table entry. And then if we increase that again, let's say 2K, become 8 page table entry. If we increase that to 4K, become 4 page table entry, something like that. Can we increase this to 8? I don't think so. Oh, but Okay, looks like we can. Alright. So as long as it is the multiply of page size, as long as the address space is the multiply of address space see this one, address space must be a multiple of the page size. Okay, thing like that. But if we provide 9k, we cannot do that and cut this error. Address space must be a multiply of the page size. Something like that. Yeah, I'm assuming if we are using 10k, we also get the error. Right? Okay. Yeah, maybe let's also consider this one to page table entry. Okay, so the more we increase, if the page size increase, the page table entry will decrease, question mark. If the page size increase, the page table entry will decrease. Maybe it's something like that. The pattern that we see here. How should page table size change as the address space grow? How should page address change? Oh, hello, Andra Wines. What themes and plugin do you use for NVim? I create the color scheme myself. You can take a look at my dot file here. I'm using the vanilla Vim, so in case that matters, this one. This is my color scheme that I create. And then for the plugin that I use, the list is in this one. Yes, this is the plugin that I use. You can take a look at this. There is some fork of the plugin that I maintain myself. But yeah, let me put this. Okay, there is that. What are the advantages of Sway over i3 beside Wayland? I'm not sure. I'm using i3 right now. Yeah, this is i3, not Wayland. So yeah, I'm not really sure about what is the advantage using Sway, because I'm still using i3. Can take a look at this. I am still using i3 as my window manager. I haven't taken a look at the Wayland site yet. Something like that. Because apparently the configuration is the same. I think there is some difference. For example, wait a minute. Let me take take a look. I've done some contribution. Wait, let me. Previously to the i3 syntax hike, like I think this one, right? There is some option about pop-up during full screen. The i3 side have the all option, but the Sway doesn't have that. Let me take a look here. Pops up during full screen mode, right? i3 have the all option here, but Sway does not. So according this comment, I guess on Wayland this does not happen because the only way to open a pop-up is to attach it to a parent window. So there is some difference there, but yeah, the difference might be subtle, so just be careful about that. i3 still have an update in case anyone wondering. Yeah, i3 is still in development. Well, we can see, I guess. See, 2 days ago. Right. i3 is still in active development. In case anyone wondering, I think there is something new too, but I'm not really sure. Yeah, January 14, 2026. Yeah, I think still in active project. I guess. So there is that. There is an update. Okay, let me continue to this one. Now let's do some translation. Oh, most of the X11 window manager don't have updates anymore. Alright. Okay, yeah, I didn't know about that. Okay. Yeah, I mean, I'm only using i3, but previously I've tried Qtile and window manager, and if I remember correctly, Qtile also works in Wayland. So if you, what is it called? If you want something that works on X11 and Wayland, you might take a look at Qtile. Oh wait, I should click the documentation. Okay, this one runs as an X11 window manager or a Wayland compositor. So this is one of the window manager that works both in X11 and Wayland. Yeah, Qtile using Python. Oh, here using Hyperland. Okay. Alright. But anyway, I haven't taken a look at the Wayland side yet. Maybe at some point I will move to Wayland. But for now, X11 is still fine. It's going to continue to Wayland. Okay. Now let's do some translation. Start with some small example and change the number of bits that are allocated to the address space with this U flag. What happens as you increase the percentage of bits that are allocated in its address space? Okay, this means that we are increasing the percentage of the allocated memory address, allocated memory, I guess. Waiting for you in Wayland. Well, yeah, maybe one day, but I'm not sure when. Okay, percentage. Start with small example. What is the default generated? It is 5. Okay. Alright, let me change this to use flag here. Okay. What is it called? 0, I guess. Oh, alright. Yeah. I kinda forgot to change this one. Okay, 1K and then 16K. Alright. 1K. Oh, interesting. It is invalid. All of it is invalid, I guess. When we use 0% of the use address of the use memory. Let's verify if we are correct. Right. Everything is invalid. Okay. Something like that. And then 25%. Oh, okay. 1, 2, 3, 4, 5, 6. Okay. From the 16 paste entry, from 16 page entry, maybe let me put something like this. 0% use memory from 16 bit entry, 0 valid entry, I guess. And then with 25% use memory from 16 bit entry, there is 6 valid entry, something like that. And then let's try calculating this a little bit. Yeah, something like this. Three and x6. Okay, virtual paste number 3 from this one. What is it called? The first number, I guess, in the address in the virtual trace, and then the offset is 896. Virtual page. Okay, this is invalid, so we are just gonna do this invalid, right? And then to PC6, virtual page number 2, offset PCT, and then virtual page number 2 also invalid. So yeah, invalid, thing like that. 1E37, virtual page number 1, offset E37, and virtual page number 1 or the index 1 here is also invalid, so invalid, and then what? Oh, 0671. Interesting. Virtual page number 0 and offset 671. This one is not invalid. Page frame number how do I page frame number 9. How do I get this one? Page number 9. I think this one, right? We have this. Yeah, I kind of forgot. How do we got the page frame number again? Indeed valid the hybrid and map to physical page 6. Map to physical page 6. Oh, is this the one? Oh, wait a minute. I think it is in this one. Okay. In the example above, the page table virtual page 0 at the page table map virtual page number 0 to page frame number. This one. Oh, okay, so the last, what is it called? The last digit here on character here, maybe something like that. The virtual page number 3 to page frame number. Okay. Interesting. So maybe we should do something like this instead. And then observe in this one. Oh, okay. 61048, maybe something like that. Let me check. What is it? Hex number to decimal, maybe something. Okay. Yeah, I'm still not sure how to calculate the hexadecimal to decimal. Something like this. Oh, okay. That's a lot. Is it in the dispatch number? Okay. Let me try this. If that is the case, how do we give the offset here? Offset. Or maybe only for A. 74. Wait. Let me think. 1K, right? Okay. Previously, why we take this one as the batch frame number? Okay. Yeah, I'm still not sure about this one. Let's try the last one here first and see the result, I guess. Yeah, I'm assuming this is gonna be invalid too, because it is in the virtual page number 1. Okay, something like that. Virtual page number 10. Wait. a minute. I am completely wrong. Okay, interesting. So we are translating the decimal representation. Is that it? What? But this is virtual page number 3. And why is this virtual page number 14? What is going on? I'm confused. Okay. So to read the site from the, what is it called? From the decimal representation, or this one? Wait a minute. Let me check here. Right. Oh. Okay. But the thing is that why this one didn't use the virtual page number 12? Oh, wait. Or maybe it depends on the, what is it called? On the page size, I guess, because we are using 1K, right? And then the default for page size is 4K. So maybe we divide this, right, by 4. Oh, okay. Alright. Okay. So it looks like we are using the, what is it called? The decimal representation divided by the page size. Okay. Alright. Okay. Decimal. Like that. Yeah. I need to know how to convert the, what is it called? The hex number to decimal, I guess. Yeah, maybe I will learn then off stream. Okay, something like this. Decimal, plate frame number. divide by 1. And then offset. Yeah. How do we decide for the offset then? Let me check. 553. Okay. So is the offset also this one? Invalid, I guess. Right. Or maybe yeah, we got this one, right? Wait a minute. Let me try this, I guess. No. Wait a minute. Do we get what is it called? The bits, the address from this one. Okay, wait, let me and yeah, why is it virtual page number 10 and not 11? Is it the nearest, I guess? Maybe something like that. PC6. Wait. Oh, 3K. Maybe something like this. Oh no, not that one. Okay, plus this one, PC6. Yeah, let me calculate that, I guess. Okay, is it the same? Not really. So how do we decide that? Wait a minute. F to 6p, okay. Right. Or maybe I should reflect this too, but it's gonna be big. So how do we calculate that? How do we calculate this? Okay. Or maybe we are doing something like this. Can we do something like this here? PC6. Oh, we cannot do that. Okay. Oh, this is the calculation step. Okay. Hex calculator maybe. Okay. And PC6. Okay. So where do we cut this? No, not that one. Yeah, I'm still not sure about this one. Okay. I guess we will continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.